Combined heat and power. CHP. Part 1. What is combined heat and power, CHP? A smarter way to use energy. Combined heat and power, CHP, also known as cogeneration, is an energy-efficient technology that generates electricity and useful thermal energy from a single fuel source, typically natural gas, biogas, coal, or biomass. Instead of wasting the heat produced during electricity generation, CHP systems capture and reuse it, providing both power and heat in one integrated system. Traditional power versus CHP. To understand CHP, it helps to first look at how traditional power plants work. In most conventional power systems, fuel is burned to produce electricity. About 2/3 of the fuel's energy is lost as waste heat, often expelled through cooling towers or exhaust stacks. The remaining third is converted into electricity. In contrast, a CHP system captures much of that wasted heat, uses it for heating, hot water, or even cooling via absorption chillers, can achieve efficiencies of 60 to 80% or more, compared to 30 to 40% for conventional systems. How it works, the basics. Here's a simplified breakdown of how a CHP system functions. Fuel in. A fuel source, e.g. natural gas, is used to drive a prime mover like a gas turbine, steam turbine, or engine. Electricity out. The prime mover generates electricity. Heat recovery. Instead of letting the heat escape, the system recovers it, often via a heat recovery steam generator, HRSG, or heat exchanger. Thermal energy use. The captured heat is used on-site for space heating, water heating, or industrial processes. This combined production drastically reduces the need for separate heating systems and grid electricity. Where CHP is used. CHP isn't a one-size-fits-all solution, but it fits many. You'll find it in universities and hospitals for campus-wide heating and cooling. Industrial plants, where both process heat and electricity are needed. Commercial buildings and hotels. Greenhouses and wastewater treatment facilities. Microgrids and district energy systems. Some systems are the size of a large refrigerator, known as micro-CHP, while others power entire urban areas. Why CHP matters today. In an age of rising energy costs, climate concerns, and grid instability, CHP offers unique advantages. Energy efficiency. Less fuel burned, more energy used. Reduced emissions. Lower carbon footprint compared to separate heat and power generation. Resilience. On-site power generation means reduced reliance on the grid. Economic benefits. Lower utility bills and potential revenue from selling excess electricity. In short, CHP is a practical step toward decentralized, efficient, and sustainable energy systems. Part 2. History and evolution of CHP. A legacy of efficiency. The idea behind combined heat and power, CHP, isn't new. In fact, it's one of the oldest and most intuitive uses of fuel. Use every bit of energy you can get. Before national electric grids, before smart meters, and long before climate change became a household term, CHP was already quietly delivering efficient energy where it was needed most. The early days, steam and industry. CHP finds its roots in the Industrial Revolution of the late 18th and early 19th centuries. Factories and mills burned coal or wood to produce steam. That steam powered mechanical engines and was also used for heating buildings and industrial processes. This was essentially the first form of cogeneration, though it wasn't called that at the time. Thomas Edison's Pearl Street Station in New York City, 1882, is a landmark in CHP history. It produced both electricity and steam for nearby buildings. Delivered steam through underground pipes for heating, creating one of the earliest district heating systems. Operated at a then unheard-of efficiency of over 50%. Edison's approach proved that decentralized energy systems could serve both lighting and heating needs in dense urban areas, a concept still relevant today. Mid-20th century, the rise of the grid and the fall of local generation. In the early to mid-1900s, centralized electricity generation took over. Large power plants, coal, gas, nuclear became the standard. Electricity transmission grids expanded. Cheap fossil fuels and expanding infrastructure made centralized systems seem more convenient. As a result, CHP systems declined, especially in the U.S. Utility monopolies discouraged self-generation, and regulations favored centralized plants. 1970s energy crises, a wake-up call. The oil crises of the 1970s brought energy efficiency back into focus. Fuel prices skyrocketed. Governments realized the vulnerability of depending on foreign oil. Interest in energy conservation and efficiency reignited the push for cogeneration. Policies and programs began to support CHP again, especially in Europe and Japan, where energy costs were higher and space constraints favored local solutions. Modern CHP, smart, scalable, and strategic. From the 1990s onward, CHP has undergone a major transformation. Micro-CHP systems emerged, allowing small businesses and even homes to generate power and heat. Technological improvements in gas turbines, reciprocating engines, and fuel cells expanded the range of applications. Digital controls and smart systems made integration into building energy management systems easier. Climate change policies, carbon pricing, and incentives for clean energy further boosted adoption. Today, CHP is a major contributor to industrial energy efficiency. Core to district energy systems in Scandinavia and Eastern Europe. Used in resilient infrastructure, e.g. hospitals, military bases, data centers. Being linked with renewable energy and battery storage in advanced microgrids. A global perspective. In Denmark, more than 60% of electricity comes from CHP systems, often linked with wind power. Japan has deployed thousands of fuel cell micro-CHP units in homes. The U.S. has over 80 gigawatts of installed CHP capacity, much of it in industrial sites. Though adoption varies, the global trend is clear. CHP is no longer niche, but a key part of a flexible, low-carbon and resilient energy future. Part 3. Benefits of CHP systems. Why CHP makes so much sense. Combined heat and power, CHP, systems aren't just about saving fuel. They represent a smarter, cleaner, and more resilient way to produce energy. Whether you're a business owner, an energy manager, or a policymaker, the advantages of CHP stretch far beyond the bottom line. Let's explore the core benefits in detail. 1. Superior energy efficiency. At its heart, CHP is about doing more with less. Traditional power plants waste a significant portion of fuel energy as unused heat. CHP systems capture and repurpose that heat, resulting in overall system efficiency of 60 to 80%, compared to about 35% for conventional separate heat and power. Lower fuel consumption for the same output of energy. Fewer power losses from transmission and distribution, since energy is often produced near where it's used. This level of efficiency directly translates into energy savings and emissions reductions. 2. Lower operating costs. Efficiency means savings. By using less fuel and capturing more value from it, CHP systems can reduce energy bills substantially. On-site electricity generation reduces reliance on the grid and demand charges. Thermal energy production offsets the need for separate boilers or heaters. In some cases, excess electricity can be sold back to the grid. Payback periods for CHP projects often range from 3 to 7 years, depending on system size, local fuel prices, and incentives. 3. Environmental benefits. CHP systems cut emissions in 2 key ways. Less fuel burned equals fewer greenhouse gases, GHGs, especially carbon dioxide. By replacing separate heat and power systems, they also reduce criteria pollutants like NO and sulfur dioxide. When powered by renewable fuels, biogas, biomass, hydrogen, CHP can be nearly carbon neutral. Fact: the U.S. Department of Energy estimates that if CHP were expanded to 20% of generating capacity, it could reduce annual carbon dioxide emissions by over 800 million metric tons. 4. Energy resilience and reliability. CHP systems are often installed on-site, allowing critical facilities to operate during power outages, blackouts, or grid instability. Maintain services in hospitals, military bases, data centers, and wastewater treatment plants. Enhance disaster preparedness and business continuity. When combined with energy storage and microgrid technology, CHP becomes part of a powerful local energy strategy. 5. Grid support and decentralization. CHP contributes to grid reliability and peak load reduction. Produces power during high-demand periods, reducing stress on central systems. Helps balance variable renewables like solar and wind. Can operate in island mode during grid failures, providing power to specific buildings or campuses. This supports the transition to distributed energy systems and modern smart grids. 6. Economic and job creation benefits. CHP projects generate economic value beyond energy savings. Local installation, operation, and maintenance create jobs in engineering, construction, and manufacturing. Increased energy efficiency boosts industrial competitiveness. Reduces dependence on imported fuels, improving energy security. In areas with CHP incentive programs, these systems help drive clean energy markets and infrastructure upgrades. 7. Regulatory and policy alignment. CHP aligns with many policy goals. GHG reduction targets and clean energy mandates. Energy efficiency standards and climate action plans. Infrastructure resilience and grid modernization initiatives. Because of this, many regions offer tax credits, grants, and performance-based incentives to support CHP deployment. In summary, CHP is more than an efficient engine. It's a strategic energy solution. Its benefits touch every corner of modern energy thinking. Efficiency, savings, resilience, sustainability. Whether in an industrial plant or a university campus, CHP systems represent how energy should work in the 21st century: intelligent, integrated, and impactful. Part 4. Basic concepts and terminology. Speaking the language of CHP. If you're going to work with or even just understand combined heat and power, CHP systems, there's some jargon you'll want to know. This part covers the foundational concepts, acronyms, and terminology that you'll see throughout this course and in the broader world of cogeneration. Let's break it down. CHP, combined heat and power, cogeneration. CHP and cogeneration are used interchangeably. They refer to the simultaneous production of electricity and useful heat from a single fuel source. CHP improves energy efficiency by utilizing heat that would otherwise be wasted. 2. Prime mover. The prime mover is the engine or turbine that generates mechanical energy, which is then converted into electricity. It's the core of the CHP system. Common types: reciprocating engine, e.g. internal combustion engine; gas turbine; steam turbine; microturbine; fuel cell, not a mechanical engine, but still generates electricity and heat. 3. Heat recovery system. This is what captures and uses the heat that would typically be wasted. It often includes a heat recovery steam generator, HRSG, produces steam from hot exhaust gases. Heat exchanger, transfers thermal energy to a building's hot water or heating system. 4. CHP efficiency metrics. Understanding CHP's performance means knowing a few key efficiency terms. Electrical efficiency, ratio of electricity output to fuel input. Thermal efficiency, ratio of useful heat output to fuel input. Total system efficiency, the combined electrical and thermal efficiency. CHP systems often reach 60 to 80%, far above conventional systems. Example: if a system converts 35% of fuel into electricity and 45% into useful heat, its total efficiency is 80%. 5. Combined cycle versus CHP. Combined cycle plants use a gas turbine plus a steam turbine to generate more electricity, not necessarily heat for external use. CHP systems use captured heat for on-site or nearby use in buildings, processes, or district energy systems. 6. Trigeneration, CCHP. Also known as combined cooling, heat, and power, CCHP. Uses waste heat to drive absorption chillers, producing cooling in addition to heat and power. Common in hospitals, data centers, and tropical climates. 7. Thermal load. The thermal load is the heating or cooling demand of the facility. A well-designed CHP system is often sized to meet the thermal load, since it's harder to store or dump excess heat than it is to sell extra electricity. 8. Fuel types. CHP systems are fuel flexible. Common sources include natural gas, most widely used, biogas from landfills or digesters, biomass, coal, hydrogen, diesel or fuel oil in backup resilient systems. 9. Grid-connected versus island mode. Grid-connected, the CHP system is synchronized with the main power grid. Island mode, the system can operate independently during outages, critical for resilience. Some CHP systems are designed to automatically switch to island mode when the grid goes down. 10. Load following, base loading. These are control strategies for how the CHP system matches energy demand. Base load runs at constant output, meeting the facility's minimum thermal or electric needs. Load following adjusts output in real time to match changing demands. Choosing the right strategy depends on the facility's energy profile and goals. 11. Heat-to-power ratio. A key design metric, the ratio of useful thermal output to electricity produced. Helps determine the right type of system and configuration. Example: a facility with high heat needs and low electric demand might favor a system with a high heat-to-power ratio. 12. Black start capability. Refers to a CHP system's ability to start up without external power. Critical for emergency systems and disaster preparedness. Now that you've got the lingo down, you're ready to dive deeper. These terms are the backbone of CHP discussions, whether you're analyzing system design, calculating payback, or debating policy. Understanding them means you can speak confidently about CHP projects, evaluate system specs and proposals, communicate clearly with engineers, energy managers, and regulators. Part 5. Key components of CHP systems. What makes a CHP system tick? A CHP system is a highly engineered combination of technologies that work together to generate electricity and capture usable heat. While configurations vary depending on size, purpose, and fuel source, most systems are built around a core set of components. This part walks you through each major piece of the puzzle. 1. Prime mover, electric generator engine. The prime mover is the heart of a CHP system, responsible for turning fuel into mechanical energy, which is then converted to electricity. Types of prime movers. 2. Heat recovery unit. This component captures the waste heat from the prime mover and redirects it for productive use. Heat recovery steam generator, HRSG, converts hot exhaust gases into steam. Heat exchanger transfers heat to hot water systems, building heat or industrial processes. These systems are designed to maximize thermal efficiency while minimizing energy losses. 3. Generate. Connected to the prime mover, this component converts mechanical energy into electricity. Depending on the engine type, it may be an alternator, AC power, a DC generator, for battery systems or specific industrial uses. Most CHP systems generate three-phase AC power, suitable for grid or facility use. 4. Control system. A CHP system is only as good as its brain. The control system manages startup and shutdown, load balancing, matching output to demand, fuel flow and engine speed, switching between island and grid-connected modes, safety and alarms. Modern control systems often include remote monitoring, predictive maintenance alerts, and smart integration with building energy management systems, BMS. 5. Thermal distribution system. The useful heat generated must be delivered where it's needed. This includes hot water piping or steam lines, district heating networks, absorption chillers for trigeneration, heat storage tanks to buffer peak demand. Proper thermal distribution is critical to achieving high overall efficiency. 6. Auxiliary systems. CHP setups often include additional systems that support safe, stable, and continuous operation. Fuel handling and delivery, e.g., gas compression, biomass feeding. Emissions control systems, e.g., selective catalytic reduction for NO. Cooling systems, for the engine or generator itself. Backup or bypass boilers, for heat when the CHP unit is down. 7. Instrumentation and monitoring. Sensors and meters help track fuel input, natural gas, biogas, etc. Electricity output, kW or MW. Heat output, BTU or MWH thermal. System efficiency and runtime. Emissions and compliance data. Data collection is essential for operations, reporting, and qualifying for energy incentives or carbon credits. Example, a mid-size CHP system layout. Imagine a CHP system serving a hospital. A reciprocating engine runs on natural gas. A generator provides 500 kilowatts of electricity to the building. A heat exchanger captures engine exhaust to produce hot water for space heating and sterilization. The system includes automatic switchover to island mode in the event of a power outage. Monitoring software displays energy usage and fuel efficiency in real time. This configuration might have a total system efficiency around 75%, a massive improvement over separate generation. Every CHP system is different, but they all rely on the same fundamental components working in harmony. Think of it like a hybrid car for your building, generating electricity, capturing waste energy, and delivering performance, savings, and sustainability. Part 6. Types of CHP technologies. One goal, many paths. While all combined heat and power, CHP systems aim to generate electricity and capture useful heat from the same fuel source. How they do it varies. The prime mover technology at the heart of a CHP system determines its size, efficiency, fuel flexibility, cost, suitability for different applications. This part covers the 5 main types of CHP systems and helps you understand when and why to choose one over another. 1. Reciprocating engine CHP systems. How it works. Uses an internal combustion engine, like in cars or trucks, to drive a generator. Hot exhaust gases and engine coolant are used for heat recovery. Key features. Power range, 50 kilowatts to 5 megawatts. High electrical efficiency, 30 to 45%. Quick startup and shutdown. Advantages. A. Low capital cost. B. High part load efficiency. C. Simple maintenance. D. Ideal for peaking or load following. Drawbacks. A. Noisy. B. Limited heat output temperature. C. Not suitable for very large facilities. Best for hospitals, schools, small to medium industrial plants, commercial buildings. 2. Gas turbine CHP systems. How it works. Burns natural gas or other fuels to spin a turbine that drives a generator. Very hot exhaust, up to 1000 degrees Celsius, used to generate steam or hot water. Key features. Power range, 500 kilowatts to 50 plus MW. High thermal output. Operates best at full load. Advantages. A higher heat-to-power ratio. B. Suitable for steam-demanding processes. C. Lower emissions than reciprocating engines. Drawbacks. A. Lower electrical efficiency, -25 to 35%. B. Not as efficient at partial loads. C. Higher capital cost. Best for industrial plants with high steam demand, district heating systems, universities, and large commercial campuses. 3. Steam turbine CHP systems. How it works. Requires high-pressure steam from a boiler, not part of the CHP system itself. Steam expands in the turbine, generating electricity. Low-pressure steam used for heating or processes. Key features. Power range, 500 kilowatts to 200 plus MW. Low electrical efficiency, -10 to 15%, but heat recovery is high. Advantages. A. Very high thermal output. B. Long lifespan. C. Suitable for large-scale heat users. Drawbacks. A. Needs existing steam infrastructure. B. Slow startup. C. Not efficient for electricity alone. Best for refineries, pulp and paper mills, chemical plants, combined with biomass or waste heat boilers. 4. Fuel cell CHP systems. How it works. Converts hydrogen or natural gas into electricity through an electrochemical reaction, not combustion. Heat is captured from the process. Key features. Power range, 5 kilowatts to 3 megawatts. High electrical efficiency, 40 to 60%. Near zero emissions. Advantages. A. Quiet and compact. B. Very low emissions. C. Excellent for areas with strict environmental standards. Drawbacks. A. Expensive. B. Requires clean, high-purity fuel. C. Limited commercial maturity. Best for office buildings, residential buildings, micro CHP, data centers, LEED certified or green buildings. 5. Microturbine CHP systems. How it works. Small gas turbine spins at very high speed. Exhaust heat used in a heat exchanger for water or space heating. Key features. Power range, 30 kilowatts to 500 kilowatts. Compact and modular. Can be stacked for scale. Advantages. A. Low maintenance. B. Low emissions. C. Easy integration into existing systems. Drawbacks. A. Lower efficiency than larger turbines. B. Sensitive to fuel impurities. Best for small commercial buildings, restaurants, light industrial facilities, buildings with steady heat and electric loads. Technology comparison table. Final thoughts. Choosing the right CHP technology depends on a mix of factors. Your load profile, electric versus thermal. Facility size. Available fuels. Budget and emissions priorities. Grid reliability needs. No one-size-fits-all solution exists, But knowing what each system can do allows you to make the right decision for your building, business, or community. Part 7. System Sizing and Design Considerations. Getting it just right. Designing a combined heat and power (CHP) system is part art, part science. The goal isn't just to install the biggest or most efficient system. It's to match the system to your facility's actual energy needs, fuel availability, and operational goals. Oversizing leads to wasted investment and underperformance. Undersizing can leave you dependent on the grid or supplemental heating systems. Let's walk through how to get it right. Step 1. Define project goals. Before diving into numbers and specs, you need to define your objectives. These might include lowering energy costs, reducing emissions, increasing resilience, replacing aging boilers or generators, qualifying for tax incentives or grants, supporting sustainability branding or ESG goals. Your system design should align with what you care most about. Step 2. Analyze energy load profiles. This is the foundation of smart CHP sizing. You'll need hourly or 15-minute interval data on electricity demand, kW or MW, thermal demand, heating, hot water, steam, cooling demand for trigeneration projects. Look for patterns. Is demand steady or variable? Are thermal and electric loads coincident? Are there seasonal swings? Do you have a consistent base load? Rule of thumb: size your CHP system to meet the minimum thermal load. You can sell extra electricity to the grid more easily than dump excess heat. Step 3. Choose a load strategy. There are two main approaches. 1. Thermal load following, TLF. CHP system is sized to meet the building's thermal baseload. Maximizes heat recovery and system efficiency. Excess electricity is either sold or curtailed. 2. Electric load following, ELF. CHP system tracks electricity demand. Heat output varies depending on electrical output. May require dump loads or backup boilers to handle heat imbalance. Some systems use a hybrid strategy, adjusting output dynamically based on real-time energy needs. Step 4. Evaluate fuel supply and type. Fuel availability directly impacts feasibility. Ask: is natural gas available and affordable? Do you have access to biogas, biomass, or hydrogen? Is fuel storage needed for propane or diesel? Is fuel pricing volatile or subject to regulation? Your fuel type also determines emissions, maintenance needs, and CHP technology options. Step 5. Select prime mover and technology. Based on your load, fuel, space, and budget. Reciprocating engines, right pointing arrow, best for smaller, consistent loads. Gas turbines, right pointing arrow, great for larger facilities with high heat needs. Steam turbines, right pointing arrow, ideal if you already produce high pressure steam. Fuel cells or microturbines, right pointing arrow, best for clean, small scale, or green projects. Step 6. Consider physical and technical constraints. Every facility has practical limits. Look at space availability, indoor, outdoor, noise restrictions, utility interconnection requirements, emissions permitting, access for maintenance and fuel delivery. Sometimes, modular systems or containerized CHP units are the best fit when space or zoning is tight. Step 7. Financial modeling and payback. A smart design is a financially sound one. Run detailed calculations for capital costs, equipment plus installation, operating costs, fuel, maintenance, staff, energy savings based on local utility rates, incentives and grants, simple payback period, net present value, NPV or IRR. Typical simple payback, 3 to 7 years for well-sized, well-run systems. Step 8. Plan for future expansion or load growth. Will your building or campus grow in the next 5 to 10 years? Consider Installing a system with modular capacity. Designing for future fuel flexibility. Integrating with microgrids or battery storage down the line. Example, sizing a CHP system for a university. Electric load, 1.8 to 2.2 megawatts, peaks during day, drops at night. Thermal load, 8,000 to 10,000 MBTU per day, very consistent year-round. CHP configuration, 2 1-megawatt gas engines with heat recovery units. Design strategy, size to meet minimum thermal load. Expected payback, 5.1 years. Carbon dioxide reduction, minus 3,000 metric ton per year. Proper sizing is the linchpin of CHP success. It requires a careful blend of data analysis, engineering insight, and real-world awareness of your site and goals. Designing around your thermal baseload, choosing the right prime mover, and aligning with utility rates and incentives will give you a system that delivers savings, resilience, and sustainability for years to come. Part 8. Integration with existing systems. The real magic, seamless operation. Installing a combined heat and power CHP unit is only half the story. The real challenge and opportunity comes with integration. A well-integrated system becomes invisible. It just works reliably and efficiently alongside your existing utilities. This part breaks down the key integration areas: electrical, thermal, control, and environmental. 1. Electrical integration. Connection options. Grid-connected parallel mode CHP system runs alongside the utility grid. Can export excess electricity to the grid, if permitted. Typically requires synchronization, protective relays, and utility coordination. Island mode standalone system runs independently of the grid. Powers critical loads during outages. Needs automatic transfer switches, ATS, and load balancing controls. Dual mode, switchable, best of both worlds, grid-tied during normal operation, islands during outages. Key considerations. Power quality, harmonics, voltage, and frequency must match utility standards. Interconnection agreements vary by utility, may require costly upgrades or approvals. Net metering and export tariffs. Some areas allow selling excess power, others don't. Tip: design for critical load coverage first, then assess if grid export makes economic sense. 2. Thermal integration. Where does the heat go? Recovered heat can be used for space heating, hot water, steam for industrial processes, absorption chillers for cooling, trigeneration, thermal storage tanks, buffer for demand swings. Thermal integration strategies. Direct connection. Heat exchanger feeds into building's hot water loop. Cascading loads. Prioritize high-temp users first, then low-temp systems. Backup boilers. Kick in when CHP can't meet peak thermal load. Control is crucial. Use modulating valves, sensors, and automated control systems to regulate flow and prevent overheating or underutilization. Think of the CHP system as a smart boiler that also happens to produce electricity. 3. Control system integration. A smart CHP system needs to talk to your building and utility systems. This means integrating Building Energy Management System, BEMS, Supervisory Control and Data Acquisition, SCADA, On-site generation control platforms, Remote monitoring dashboards. Capabilities. Load following. Adjust output based on demand. Automated fault detection. Demand response participation. Predictive maintenance alerts. Pro tip: use an open protocol like BACnet or Modbus to ensure future compatibility. 4. Safety and environmental integration. You'll also need to build around emissions controls, SCR, oxidation catalysts, noise attenuation systems, ventilation and exhaust management, fire suppression and leak detection, fuel safety compliance for natural gas, propane, etc. Regulatory considerations. Air quality permits. Noise ordinances. Fire codes. Utility grid safety rules, IEE 1547, UL 1741. 5. Physical site integration. Even if a system performs well on paper, physical layout issues can be deal breakers. Check for space constraints, especially in retrofits. Access for maintenance or fuel delivery. Weight load-bearing limits. Ventilation for engine or turbine cooling. Pipe routing for hot water or steam. Containerized CHP systems offer plug-and-play options where indoor space is limited. Real-world example, hotel retrofit. A 200-room hotel in a downtown area retrofits a 500 kilowatt CHP unit. Integrates with existing hot water loop for showers, laundry, and pool. Electrical output offsets 60% of daily usage, staying grid connected. Smart controls linked to hotel BMS. Ventilation system added to handle rooftop unit heat exhaust. Estimated energy savings, minus $180,000 per year. Payback period, 4.3 years. Keys to smooth integration. Integration isn't just an engineering task, it's a strategic challenge. The best CHP projects work with what you've got, improving resilience and efficiency without disrupting operations. Whether you're building from scratch or retrofitting an old facility, smart integration makes CHP invisible but invaluable. Part 9. Economic analysis and financing options. CHP is an investment, not just infrastructure. A combined heat and power CHP system is more than a piece of equipment, it's a long-term investment. The right project can yield double-digit returns, improve energy independence, and protect against future utility rate hikes. But to make smart decisions, you need a solid economic analysis and often creative financing. 1. Key cost components. Capital cost (CapEx). Equipment, CHP unit, heat recovery, control systems. Installation, construction, electrical, piping, ventilation. Engineering and permitting, site assessments, permits, interconnection. Commissioning, startup testing and tuning. Range, $1,000 to $4,000 per kilowatt installed, depending on size and complexity. Operating costs, OPEX. Fuel, biggest ongoing expense, usually natural gas. Maintenance, varies by system type, fuel cells and turbines usually more than engines. Staffing, for larger systems, might require on-site operators or remote monitoring. Replacement parts, especially for engines after 5 to 10 years. 2. Estimating, financial performance. Basic metrics. Typical payback, 3 to 7 years, IRR target, greater than 12 to 15% is considered strong for CHP. 3. Example CHP financial case. Medium manufacturing plant. CHP size, 1.2 megawatts gas engine. CapEx, $2.4 million. Fuel cost, $4 MMBTU natural gas. Electricity rate offset, 13 cents per kilowatt hour. Annual savings, $380,000. Payback period, minus 6.3 years. NPV over 15 years, $1.9 million. IRR, 14.6%. 4. Funding and financing options. Not every company has cash on hand for a big CHP investment. That's where creative financing comes in. A. Self-financing cash purchase. Full control and ownership. All savings go to you. Large upfront cost. B. Energy performance contract, EPC. Third-party energy company installs system. You pay from guaranteed energy savings. Common with public and institutional clients. C. Power purchase agreement, PPA. A third party owns and operates the CHP system. You buy electricity and heat at a fixed rate. No upfront cost. Less control, longer commitment. D. Leasing or equipment financing. Similar to leasing a vehicle. Fixed monthly payments over 5 to 15 years. Predictable cash flow, potential tax benefits. 5. Incentives and grants. Federal, state, and local incentives can dramatically improve economics. Examples: investment tax credit, ITC, up to 10% for qualifying CHP systems US. MACRS depreciation, accelerated depreciation for equipment. State grants and rebates, NYSERDA, California SGIP, etc. Utility programs, demand reduction and peak shaving bonuses. Tip: stackable incentives can shave 30 to 50% off CapEx in some regions. 6. Operating contracts and risk sharing. Many CHP developers now offer performance-based contracts. You pay only for verified energy output. Service agreements covers parts, maintenance, and remote monitoring. Fuel supply contracts lock in gas prices long-term. These can reduce financial risk and make budgeting easier. 7. Sensitivity analysis. Because energy markets change, smart financial models should test fuel price volatility, electricity rate shifts, maintenance cost increases, partial system downtime, changes in thermal electric demand. This helps you prepare for best and worst case scenarios. Summary table, CHP Economics Cheat Sheet. Part 10. Operation and Maintenance, O&M. Beyond installation, the daily grind. Installing a combined heat and power, CHP system is just the beginning. Like any piece of high-performance equipment, it needs care. The secret to long-term savings and performance. A proactive, structured maintenance strategy. 1. Why O&M matters. Without proper O&M, efficiency drops. Downtime increases. Repairs get more expensive. Fuel consumption goes up. Emissions and compliance risks rise. With good O&M, your system hums along for 15 to 25 years. You get predictable energy savings. You reduce unplanned outages. Total cost of ownership stays low. CHP isn't set it and forget it, but it doesn't need to be a headache either. 2. Key components needing maintenance. Depending on your system type, here's what needs ongoing care. 3. Typical O&M schedule. Here's a general idea of how often tasks are performed for a reciprocating engine-based CHP. Many vendors offer maintenance contracts that cover most of this. 4. Staffing and support models. In-house O&M. Requires trained technicians. Good for large facilities or campuses. Higher upfront cost, lower per year cost long-term. Outsourced O&M service agreement. Third party handles all maintenance. SLA guarantees for uptime, efficiency, emissions. Great for small-medium systems or those without energy staff. Hybrid. On-site staff handles daily ops. External experts visit for major service or tune-ups. For smaller CHP systems, less than 500 kilowatts, remote monitoring and automated alerts can replace on-site staff. 5. Monitoring and performance tracking. What to monitor? Electric output, kW. Thermal output, BTU per hour. Fuel input, MMBTU. System efficiency, %. Runtime, hours. Downtime events. Emissions compliance data. Tools and software. SCADA systems. Web-based dashboards. Predictive maintenance software, AI-driven alerts. Proactive monitoring can prevent 80% of costly breakdowns. 6. Common O&M issues. 7. O&M costs, what to expect. Estimated annual O&M costs. These numbers include labor, Parts, fluids, testing, remote monitoring if used. For a 1 megawatt CHP system, $70,000 to $150,000 per year typical. 8. Building a resilient O&M plan. Your plan should include clear SOPs, standard operating procedures, emergency protocols, fire, failure, utility outage, vendor contact list, spare parts inventory, maintenance logs, and digital backups. Budget for overhauls, e.g., every 7 to 10 years. Real-world snapshot, University CHP. System, 2.5 megawatts gas engine plus heat recovery, O&M approach, hybrid, on-site staff plus quarterly third-party service, downtime per year, less than 1.2% annual O&M cost, minus $0.018 per kilowatt-hour. Benefits, runs 24/7 offsetting 65% of campus energy use. Upgrades, software tuning led to 4% efficiency gain in year 3. Operation and maintenance aren't just about keeping the lights on, they're about safeguarding your investment. Whether you're running a hospital, university, hotel, or factory, a smart O&M strategy ensures your CHP system performs like a champ for decades.